Hey, good evening, this is Tiger. Welcome to my stream. Good evening to you, AJ. Thank you for the first entry in the chat, and welcome everybody to tonight's stream. I thought it is time now to actually fill a gap in our collection of videos, especially the ones about brakes and brake systems. We have talked about air brakes, we've talked about EP brakes, and even about eddy current brakes, but what we have not really talked about so far are the electrodynamic brakes, the dynamics or the E-Bremse. And I think 2 weeks ago we talked about, can we use dynamic brakes in neutral section? Juniper, hey, nice to see you on the chat. And I think it is time to look into that and find out what we can find out about dynamic brakes. Spectre, hey, good evening to you. They come in a lot of different varieties, and they are great, but you need to do what you need to know what to do with them. And I'm going to try something special today, because you can see I already put up Train Sim 5 Sherman Hill caption. I will take you to Cheyenne Yard, and JG Irish or J Irish 19, guten Abend, you say. Guten Abend to you, good evening to you, lofty evening Tiger, he says, great to see you guys. So since you said guten Abend, I think I read this as J Girish. Correct me if that's wrong. Yeah, you can hear the noise. It is so loud because I put together a collection of locomotives here in the yard at Sherman Hill. You can see it around the turntable, to demonstrate what a great variety of different installations electric brakes can have. And probably the first instance of dynamic brakes that we all came across was something like this on Sampage Crate. At least that was the first locomotive that I drove, not the one with the Union Pacific livery here, but something that looked like this, with this setup of a brake valve, with the auto brake for the train brake, with the independent brake lever, and with a special lever here that looked a bit like an inverted throttle for the, as it says, dynamic brake. Always with a caution, do not move dynamic brake to set up until throttle has been in idle for 10 seconds. AJ Black subscribed. They've subscribed for 19 months currently on a 19-month streak. Thank you so much, AJ, for doing this. And yeah, this might have been the first that most of us came across a dynamic brake. At least that was the first that I came across a dynamic brake. Didn't have no clue how to use it when I first played Sampage Crate in Train Sim 2 at the time. And still, it is here. It can be used as soon as we put our reverser to forward or reverse, and not actually notching. Even if we have something like notches, we can use it for dynamic braking. Next to our 26C brake valve here and our independent brake. But not all installations or instances of dynamic brakes look as clear-cut as that. For example, the SD40 that you can find in Clinchfield. If you sit down here in this beautifully, whatever this color's name might be, cap, you look around for a lever for the dynamic brake. You find your lever for the automatic brake, the lever for the indie brake, your throttle. Everything looks like normal, but there is no lever for the dynamic brake. Instead we have this, the selector level. And on these older locomotive, you have this selector lever, typically to set your transitioning status, and if you reverse it beyond the off section, you get to this ominous section of B, what turns your throttle all of a sudden into the lever for the dynamic brake. So very clever. Nobody's telling you this if you're running those locomotives in Clinchfield, probably. And nevertheless, this is how you can get dynamic braking in a locomotive like this. And then you use your throttle to use it. You can see how it turns into a percentage, not in a notch. If you have it on a transition selection that allows you to go, you have notches that operate your diesel engine. And then there are even locomotives like here, the GP9 from Canadian National, from the Oakville subdivision. If you sit in the driver's seat here and look for the dynamic brake, for the dynamic brake, you don't find any. So not all locomotives necessarily need to have a dynamic brake, and this specific version of the GP9, as far as I know, does not have one. So you just have to use your air brakes to slow down. And to spoil one thing, we have looked at American locomotives all the time. If you go through your British diesel locomotives, for example, even though they are diesel electric locomotives, you will be hard put finding one with a dynamic brake, because British locomotives typically do not have dynamic brakes for whatever reason. At least not until very recently. British vehicles had to put up without dynamic braking. We will see some of them who have. Inspector says, I hear the GP9 is bullied by the other locos for that and for its size. Well, the poor GP9 is always bullied, but nevertheless, it will stand its ground, and at least it has been around for much longer than the other locomotives have, or at least most of them. And this is a lifespan that the other locomotives still have to achieve. At this point, before we look at the other locomotives here, let's go into our presentation that I prepared for the dynamic brake. I put an electrodynamic brake in front of it because there is a different kind of dynamic brake, the hydrodynamic brake, that we already have talked about in connection with retarders and turbo reversers. You might remember that it's already quite some time ago that we played with the Voslo G6 on Rhein-Ruhr-Ost, a scenario where we had to save a train that was stalled there on the incline, and there were some rather weird signaling things and stuff, and there we talked about the hydrodynamic braking retarder that you can also find on many trucks. If you play American or European truck simulator, you can use the retarder, and that is something like quite the same hydrodynamic. But this is not what we're talking about today. We're talking about electrodynamic brakes. This is why you sometimes have the name dynamic brakes in the US mainly, and in continental Europe more like electric brake. In Great Britain typically you have more like the distinction between rheostatic and regenerative braking, but we will get to this and how those terms all fit together. First, let's see how it works, this stuff. And for that, we have to think back on how we actually propel our locomotive. And diesel electric locomotives or electric locomotives have in common that they use driving motors, typically on the axles. We have talked about last week how we know from wheel classification systems on what axle we actually have those driving motors. If we have driving motors, which of them are only idlers, typically on a bow locomotive or a bow prime or BB locomotive like I have here, you would have 4 powered axles distributed among 2 bogies, and I only indicated the driving motors here on this front bogie. Then you would, on a diesel electric motive, have your diesel engine, what is the prime mover, and the job of the prime mover is to turn a shaft, and the shaft then turns a generator or an alternator, depending on whether you want DC or AC current, and you create a current, and this current is then used to feed the driving motors and to turn the axles and the wheels, and then your locomotive is moving. If you use an electric motor, a locomotive or a vehicle, then you either have a pantograph or a shoe for the third rail. I only pictured the pantograph here, and then typically a transformer and a lot of other electric gadgets, and then you get the juice directly from the overhead catenary, feed it through the driving motors, and then back into the rail. What is the cable, if you want it like this, that takes the juice back to the power station, so that you have a closed circuit between the power station, overhead catenary, pantograph, vehicle, driving motors, and then rail back to the substation where the energy is provided into the net. You can have both on your locomotive. Also, that is possible. Multi-system locomotives, or at least a smaller prime mover for emergency applications like the Dragon 2 in SimRail that we have seen, and then you can switch between both possibilities. They all have in common electric and diesel electric locomotives that you use driving motors on the axles, and there we have talked about the simpler and older form of a commutator motor that can be a DC motor or a one-phase AC motor as well, where you have like a rotor that is a piece of metal like an anchor, and you have your current in a coil wound around it, and here with brushes, commutators, so that the cable does not get twirled around the rotor. You put it on an axle, and then you use the current to create a magnetic field in the stator, and as soon as you have your current flowing, then you create a magnetic field in the rotor, you create a magnetic field in the stator, and then the whole thing starts turning. That was our commutator traction motor as DC or even AC, one-phase AC, Reihenschlussmotoren, universal motors, what is more or less the older version of that. We have already talked. CD Radar, see you on the chat. Great to see you and have a good evening. We also talked about what we have on the modern locomotives, Drehstromlokomotiven, AC inductor motors, like on the Vectron, for example. We have our not one stator, but we have more coils aligned around one axle in the middle, so that we can, you remember that from the stream about the AC induction motors, we can create the illusion of a rotating magnetic field, and that induces a current in our squirrel cage, what we have for a rotor in this locomotive, or in this kind of motor, and then we have a magnetic field with the illusion of rotating around the middle here, and we have a different magnetic field induced in our squirrel cage here, and this is always lagging behind and can never catch up, and is turning slower than the magnetic field is seemingly rotating around it. It has a slip, what is important, otherwise we could not create an induction current. We could not induce a current in the squirrel cage, and those are our AC traction motors. Asynchronous because the thing in the middle is turning slower than the magnetic field seems to rotate. Induction because we induce our current in the squirrel cage by means of the seemingly rotating field. What makes it possible to get rid of those brushes of the commutators, so we don't have mechanically moving parts here that are subject to wear and tear. So this is the big or one of the big advantages of this kind of motor, apart from that it can be controlled more easily with VFs, with variable frequency and voltage drives. And squirrel cage, because that thing in the middle, if you look at it from 90 degrees around, it looks a bit like a squirrel cage, like those things where you can have a hamster or a squirrel running inside, and then they can run even though they are in a little cage. So the idea of both those contraptions is that we have an electric current running through our wire, that we create magnetic fields with magnetic flux. And if we combine that, you might remember that from high school and physics, and the rule of the left hand and the rule of the right hand with thumb and index and middle finger, and that creates movement. Moving a wire in the magnetic field creates electric current. Having electric current running through a wire in a magnetic field results in movement, and combining the electric current with the magnetic field creating movement is the principle of a motor. And the really great thing about this, and now we're getting closer to the dynamic brakes, is that this thing works the other way around as well. If we have movement already, like our train is running downhill, so that we can use gravity and inertia to turn our wheels. We don't need to power them anymore, we are running downhill anyway, so we have the movement. We just have to provide the magnetic field, and what we come up with is electric current. That does not take any physical modifications of our motors, not with the commutator traction motor, not with the AC traction motor. We just have to do a bit of switching, typically change the polarity of what we connect the motors with, and then we can not make movement out of electric current and magnetic flux, but we can make electric current out of movement and magnetic flux. And that is the principle of a generator. What typically happens here in the generator, movement from the prime mover combined with a magnetic field results in electric current, and this is now what is happening in our driving motors. So again, everyone who is really apt with this science stuff and technical engineering stuff, electrical engineering stuff, please don't crucify me for putting things so simple, but it is, I'm not a technical person. I want to understand the principles, and this is how I understand the principles, and this is why I'm discussing it like this here. So the great thing about our driving motors is that we can just reverse the process and not use it to power the train, but use the movement of the train to create electric current. But why do we want to create electric current? Because if we are drawing the electric current out of our wheels, we are slowing them down. And this is the idea of the electrodynamic brake. We get the energy, the kinetic energy of the train out of the train and the wheels by converting this kinetic energy into the electric energy that runs with our current, and we can draw it out of our wheels and the train and slow it down this way. That is all great. The problem is that we have to get this electric current somewhere. We cannot just have it run around in our locomotive. That does not work. And if we cannot get rid of the electric current, then we cannot slow down the train. And for that there are different concepts and different ideas what to do with the electric current so that we can actually slow down the train by converting the kinetic energy into this electric energy. And all this is under the roof of electrodynamic braking. In German, E-Bremse, elektrische Bremse, electric brake, what is more or less all the same idea. And now the two big different things that run under dynamic braking. One is the rheostatic braking and one is the regenerative braking. And what is the first one? Rheostatic. Typically on a diesel electric locomotive where we do not have a connection to a power grid. So what we have to deal with our electric current that we are producing in our driving motors now on the locomotive. We cannot rely on any outside place where we can get it to. And well, if we just leave everything like we have, we would turn our motors around into generators, create an electric current. If we feed it into our generator, we can probably turn around that one too and then have a motor. Then would the generator or alternator would turn the shaft and we would turn our diesel engine backwards. That does not make a lot of sense. Unfortunately, we cannot create diesel oil out of exhaust fumes by cranking the diesel engine backwards. Engineers have come up with a lot of things, but this is, at least at the time being, not possible. So at this point here ends our possibilities to reverse the process, and we have to do something else with our current. And well, if we have to get rid of the current, one thing that we can always do, we can burn it. And for that we send it into a grid with a lot of loops, what are resistors more or less, and in those resistors the current gets converted into heat. Same principle as in a toaster, for example, in a hot air blower, in an electric heater for your room. You send the current through coils and the coils heat up through the current and the energy dissipates as heat into the room. The thing is, we don't want our locomotives to heat the landscape. It's not the idea, but here we just want to get rid of this energy. And this gets quite hot at this point in this rheostat. This is why it is called a rheostatic braking, because those resistors that turn the electric energy into thermal energy are called rheostats. And to get rid of the hot air around those rheostats so that they don't melt or set the locomotive on fire, we need fans. And those fans blow off the hot air. So on those diesel electric locomotives, like in the American variety that we have a lot in the game, we always find a lot of fans on the roof. They are not only important for cooling the prime mover, but especially for cooling those resistor grids that are used for getting rid of all the electric current that we create with our dynamic braking. That works great, but is a bloody shame, because we are just wasting all the electric current that we are producing with our electric braking. This is why clever guys came up with the idea of regenerative braking. Why can't we just use this energy for something better than heating the Allegheny Mountains on top of us? Why can we just not feed it back into the grid, for example? And this works if we have a connection to the grid, like with the pantograph or with the shoe for the third rail. And then we can just feed it back into the grid, and another train that is not braking but accelerating can use this energy instead. So we are just helping the substation to put the juice into the net. Obviously we need some electric circuitry for that to make it work, but the principle is we're not drawing the power from the grid and turning it into kinetic energy into the traction motors, but we are using the kinetic energy that we have already in our train, turn it in the traction motors, now having become a generator, into electric current, and feed it back into the grid. Works great as long as we have a connection to the grid. Well, works great. It sometimes did not work so great, but nowadays it really works quite well. And this is why we can get some energy back. And on a locomotive like the Vectron, for example, you get this in orange or yellow figures. How much energy you actually fed back into the grid, how much you used, how much you fed back, and this is where the eco driving comes in, and how you can measure how eco-friendly your driving is. So this is actually going back into the grid and is not blown into the air for no use at all. But what happens if we don't have a connection to the grid anymore because, for example, we have to lower our pantograph, or for example, there is a neutral section, and this is what we have been discussing the other day. Can we still use dynamic braking if we are in a neutral section, if the main circuit breaker is off, or if the panto is down, if we have no connection to the grid at the moment? And this totally depends on your locomotive or your train, what it can do. Some vehicles actually cannot use dynamic braking at this point if they have no connection to the grid, because then there is no point of getting of how they can get rid of the electric current that the dynamic braking would be producing. Then there are some vehicles that have a resistor grid for that, so that only for those situations where we cannot feed it back, we can still use rheostatic braking instead, and then we can use the dynamic brakes, but we lose the benefit of the regenerative braking. Not the greatest thing, but still allows us not to lose the braking effect of the dynamic braking. And if you think, for example, the Talent 1 train in the full airbag, if you run into a neutral section, switch off your main circuit breaker, you will see that once you lose your dynamic braking effort, if you have been braking with dynamic brakes at this moment with the combined power and brake handle, and then the train typically compensates this by using the air brakes to slow down. But you can see this transition on the Talent 1, for example, even on the ACS, the American City Sprint 64 in Boston Providence. If you run into the dead sections there, I think that you can, or open, no, the dead sections are not simulated, but if you open the main circuit breaker for the dead sections there, I think that you, at least that's the last time I checked it out, can see that you lose your brake effort, at least according to the controls that they show you. And then you have to use your air brakes manually to compensate for that, at least. Yeah, but this totally depends on your locomotive, on your train, and on the specific model that you're running, and sometimes even on the specific settings on your locomotive. And there are still some other ways to compensate or to use your electric current if you have no connection to the grid. And one thing would be you can charge a battery if you have one on your train. You can use the current to charge your battery. Obviously this only works up until the point when the battery is charged, and then you either have to use your resistor grid, or you have to get rid of your braking effort and use the air brakes instead. But this is also a clever thing, at least for a certain amount of current that you can store in your battery. And another very clever thing, in my opinion, is that there are some vehicles that can actually use this current to feed it into the head end power, or in the train line, all the stuff that the train is consuming. You might have actually 12, 14 cars full of passengers behind you who want warm feet, who want light, who want their phones charged, who wants their laptops powered. They have a lot of demand for electric current. So why not send this current into the train line and yeah, save the energy that you would draw from a battery or whatever in the meantime. So from what you can read, the ALP46 that you can find on New York Trenton is a locomotive that can actually feed the excess energy from dynamic braking into the train line and does not even have resistor grids anymore, because the passenger cars on those trains have such high a demand of energy that all the current from braking can be used up there. So, just recap, the electrodynamic braking comes typically in two big forms. The rheostatic braking, where we just burn the current that we are producing, transform it into heat and blow it off into the air. What is always our fallback system if we cannot do anything better with our current. If we can do something better with the current, we would use it in a regenerative way and feed it back into the grid, or if we have no connection to the grid, feed it into a battery that we have on the train or into the train line, so that we don't need to store it, but it can be just consumed by our passengers for light, for heating, for whatever they need the current and the energy for. Alright, then what did I want to talk about else? The next thing is that you might have witnessed that sometimes the trains are mixing the e-brakes, the dynamic brakes and the air brakes on their own, and this is the whole idea of brake blending. On the classic locomotives, like on Sandpatch Grade, for example, you have to do that on your own. You have to operate your 26C automatic brake valve and set a certain amount of air pressure when you're running down Sandpatch Grade, for example, and then add the dynamics. Blake branding, yes, it's lofty for my when I misspoke. It's not Blake branding, Sir Blake branding, it is brake blending, what I was talking about, yeah. And typically on the old machines you have to do this on your own. You have to mix the air brakes and the dynamics. Also in the video on Cajon Pass, when we were running down Cajon Pass there, we have to set the air brakes on a measure that just works, so that we can use the dynamic brakes to adjust the brake force that we need to get our train safely and with constant speed through a variable gradient. And on more modern trains, this is done for you by a brake computer, Bremsrechner, that calculates that. And how does it work? In principle, the thing is that if you have a diagram where you have the braking force in one direction and the speed of your train in the other direction, that classic dynamic braking, electrodynamic braking, has a curve that looks a bit like this. So if you are at 0 speed, you don't have any brake force at all, and it takes a bit, up to like 20 kilometers or something, for the dynamic brake to actually have to get into the effective range. And then if you're getting faster and faster and faster, you cannot get so much energy out of the out of your train anymore, and the effectiveness drops. With higher speeds, the effectiveness of the dynamic brake drops, and with classic dynamic brakes in the range up to 20 kilometers per hour, you don't really have effectiveness with the dynamic brakes. And in fact, it says he is the cousin of Eddy Current. Yeah, that's true. We have a lot of names and a lot of players in our brake set over here. Yeah, so that would be a classic thing. And on an old train, you have to compensate for that by adjusting your air brakes, for example. So, for example, you want to have a constant braking force and set your driver brake valve to a certain amount, 50%, for example, or notch 3 out of 7, or whatever. And on more modern trains that can do brake blending on their own, the brake computer can analyze this and say, okay, the driver wants 50% braking force, let's see where we are. And then you can see that there is a zone where the brake force that the dynamic brake is providing is just enough to provide whatever the driver wants the train to apply and brake force. And this is a speed range where the train would apply dynamic brake only. And yeah, well, then you can look at the diagram, and you can also see that there are zones where the dynamic brake effectiveness is marginally, and it does not make sense to use it at all. So typically on those older machines at any rate, there is a certain cutoff, and if the effectiveness of the dynamic brake drops below that cutoff, it is not used anymore. So in those zones between 0 and the cutoff effectiveness, speed, and exceeding a certain point in speed, we would use only the air brake. So the brake computer would only apply air brake pressure and to slow down the train, and not use the dynamic brake anymore. And in those areas in between where we still have some effectiveness, but not enough to fulfill the requirements that the driver is asking, the computer would blend. It would just compensate what the dynamic brake cannot do with air brakes. And this happens on this as well. And how can he do it? How can the computer do this? Well, it calculates. It knows how much brake effort the dynamic brake provides, and it compensates the rest by allowing air into the brake cylinders. And typically this works in a way that if the driver sets the setting to a certain percentage or a certain notch, then already the EP brakes ask for that brake force into the brake cylinders. But there is an additional valve, typically an electromagnetic valve, that can be operated in a way that if it is provided with a current, then it cuts off the airflow into the brake cylinders at this point. And the brake computer will send a current to those valves as long as the dynamic brake is effective. And if the effectiveness drops, then this valve will allow more air to actually go into the brake cylinder. So why is this installation of use? Because if for any reason we suddenly lose the dynamic brake because something breaks in our circuitry, and all of a sudden we do not have any dynamic brake effort anymore, then there will be no current to this valve anymore, and it will not stop the air from going into the brake cylinder. And then all of a sudden we do not need to modify the air brake system anymore. Only by not powering this magnetic valve anymore, we will have all the pressure that we ask for more or less instantaneously in our brake cylinder, and the air brakes take over. So how this is actually done in a pneumatic matrix is up to the vehicle in question, but the principle is air brakes are compensating for what the dynamic brake cannot do. If the dynamic brake is enough, we only use the dynamic brake because it is super, there's no friction and no wear and tear, and at a certain point where the cutoff is reached, we are only using air brake, and typically we use it in a way that the air braking force is already asked for by the system, but held back by a valve that works in a fail-safe way, that if we lose the dynamic brake effectiveness, if we lose it all of a sudden because of a malfunction, then we have very fast our brake pressure into the brake cylinders without having to lower brake pipe pressure or anything before. Yeah, this is why you should use, even when running your locomotives light, you should use your driver brake valve for braking, and probably not only using the dynamic brake in the combined lever, for example, if you have one, because then in case of a malfunction you have your air brakes faster at hand, and the other way around, you just lose your dynamic brakes, see, oh, there is nothing there, and then you have to initiate the air brakes instead. And even if the brake computer is doing this, it always takes longer, it has a higher latency as compared to you have already the air brake system ready. Yeah, that is the principle about the brake blending that you do on your own on the older machines, and what is done for you by the brake computers on more modern machines. And then on very modern machines like the Vectron, for example, you don't have this curve with the almost no effectiveness on slow speeds, but actually because of some gimmicks in the circuitry and some additional gadgets, you can have e-brake systems that work up to an effectiveness of 0 speed with enough brake force to actually stop your vehicle. With the classic brake effectiveness curve of the dynamic brakes, you would not be able to stop your train, because at 0 your effectiveness drops to 0 and you cannot hold your train. With a modern version of the e-brakes, dynamic brakes, you actually can do that, because you are using some of the energy to feed it back to hold those AC induction motors in place. That would be a bit too much to explain it here. At least we can know that we have on modern vehicles typically a dynamic brake curve that is effective up to speed 0, and that actually can hold the vehicle in place. So if you even use this in the game with the Vectron, you will see that with using the combined brake and power lever alone to slow down your train with a dynamic brake, you will be able to stop it. Even if the AFB holding brake does not kick in, you will be able to stop and hold your Vectron in place with the dynamic brake alone. Typically there are regulations that forbid you to actually hold it in place with the dynamic brake, because if you lose it suddenly, then your vehicle rolls away. So if you actually have to hold it in place, keep it stationary, you have to use air brakes or spring-loaded brakes to stop it. But technically it'd be possible to stop it and hold it with dynamic brakes of the modern variety alone. And then you would not have a blending here on the lower speeds. But what is still true is that they lose effectiveness on higher speeds. And then you can configure your locomotives in a way that they then do brake blending after that. And this is often called, if I understand this correctly, the Nachbremswirkung on the Vectron in Germany. What is, well, if you want to translate it, it is after brake effectiveness like this, or an additional braking effectiveness of the brake. It actually means that if you lose dynamic brake effort, then the air brake will add additional power. And it is an interesting piece of trivia that in Austria it is not allowed to do this. This is why the Austrian country setting on the Vectron, as far as I have seen and what William told me, if you use the Austrian setting on your Vectron, then even if you lose effectiveness with the dynamic brake, you will not have air brakes kick in and compensate. For some reason in Austria they don't want the locomotive to do this. Even if you don't have dynamic brakes on your locomotive, you only slow down with the train, with the brakes on the train, not with the locomotive. Whereas in Germany we are totally fine with the effect that if the dynamic brake drops below what we were requesting on our driver brake valve, and compensate with air brake. Yeah, that's that. Brake blending, super interesting, a gazillion of different ways to implement it and how your vehicles actually work, and it must be really difficult to implement all this on your modeled trains. And yeah, two things for using the dynamic brakes that are really crucial, especially if you're running the American locomotives with those super long freight trains, super heavy with a lot of locomotives and so on, and to decide what brakes you want to use. One thing obviously is, from what we have learned, we are slowing down the trains by means of our traction motors. That means, on the other hand, we are braking with the loco only, or with the locos only. If you have more of them that are working as multiple units in MU mode, then also the other ones, all the locomotives that can apply power typically can also apply dynamic brakes if they are working actually, but not the cars in between. Typically you don't have dynamic brakes on vehicles that are not powered. And you can see that if you're running downhill, this can result in the whole train pushing into your backside, what can be quite annoying or even dangerous. So you really need to know whether your train can do this without derailing, because just of the pressure of the unbraked trains running into your back. So sometimes it might be better to use some air brakes, because the air brakes also slow down the cars, and only use the loco brakes on the locomotive on top. We will get to this in the second thing that we have to mention here. And it also shows us why it is sometimes so important to have locomotives on the back, not only for getting the consist up the hill, but also for getting it down in a safe manner. Because if you have locomotives at the back, then also this locomotive can apply braking force, and then you don't have the weight of the whole train running into your back, but some of the weight can be held back by the locomotives at the end, and some can be well held back by the locomotives at front, so you have a lower impact on your locomotive with that. And then it can even make sense to have more locomotives in the middle, because then this effect gets even more distributed, and you have a shorter set of cars that are actually pushing or pulling on one locomotive. And you can never forget, this is one coupler in between that has to take all the strain here. This is also important, so not to apply too much dynamic brake force on the locomotive at the end if the locomotives at the front are not braking, because then the whole train is pulling on this coupler here. So always need to know whether your train can do it if you use the dynamics, and if you decide to mix them with air brakes or not. And well, we have talked about the San Bernardino train disaster of '89 quite a lot, and this is such an instructive incident, because that was a situation where you had some locomotives at the front, some locomotives at the end, and the engineer at the top did not know that on the back the dynamic brakes were not fully functioning. And this resulted in a lot of regulations in the 49 Code of Federal Regulations that required a lot of precautions to make sure that the driver of the leading engine knows how many dynamic brakes on the train are actually working, or if there are any locomotives with defective dynamic brakes, so that he can judge the braking effort that he has to apply with the air brakes, and cannot rely on the dynamic brakes. And that locomotives need to have a big sticker on their cab if the dynamic brakes are not working, and a lot more actually of regulative stuff. But this underlines how important it is to know what your dynamic brakes can do in your train, so that you know how to safely get it downhill. That's one thing. Never forget that the dynamic brakes are only working on the loco, not on the train. And the other thing is, I always remember watching a video of Matt where he explained this, because it is so important. This is your bogie. Those are your driving motors, and you use those to get the kinetic energy out of it, and they rely on the wheels turning. So what happens if you use the air brakes on the same axles? Air brakes press brake shoes against the wheel and stop them from turning. So we have two conflicting things. We need the wheels turning to actually make our motors into generators, but at the same time we are preventing them from turning, and this lowers the effectiveness of our dynamic brakes if we use our friction brakes on the same axles. That we don't want, and this is why we want to have the brake shoes away from those axles that are used for dynamic braking, and this is why we always bail off our air brakes on the locomotive. So if we apply with our 26C or whatever we have on our locomotive, our train brakes that apply brake cylinder pressure on the locomotives and the cars alike, then we will use the handle, typically the handle on our independent brake, and bail off the air brakes on the locomotives and all the vehicles that we use for dynamic braking. This is why this is so important for the effectiveness of the dynamic brakes, so that we have freely turning axles, so that we can use them for creating the current and in the process slow down the train here. On the cars, it is super that we have the brake shoes against the wheels if we need to combine it, but not on the locos. And one thing that we can not always do in the game is bailing off at the rear. Bailing off with the independent brake only works on the locomotives that are connected together. It does not work in a, at least with the locomotives that we have in the game, it does not work in a way that we can also use the on the end, for example, with the banking com. You know that in the game we simulate a second engineer on the rear locomotives, that we give orders via the radio connection. This is why we press the banking com, and then the operator, the simulated operator in the rear engine, is just copying what we are doing at the front. If you use throttle, if you use dynamic brake, it's just copying, but it does not copy if we bail off at the front, as far as what I have seen. On some locomotives you can use the external cameras to go through the window and bail off at the end. On some you can't, because for whatever reason they are built in a way that you cannot operate the controls on the inside with the external cameras. But in my opinion, it is also important to bail off at the rear, because otherwise we will have a higher efficiency of the dynamic braking at the front than we have on the rear, and then this distributing effect doesn't work that properly. Okay, this is what I wanted to tell you about the presentation today. I think electrodynamic braking is a really interesting thing. It gets very, very confusing and very, very much electric engineering wise, and the more you know about it, the more you know about your specific locomotive and the specific model, the more you can actually enjoy them and use them. Spectre says, I always wondered whether that would be simulated and how the settings of the rear loco would have to be, so now never mind. The bail off. Actually, on some locomotives you can bail off. If you have more of them, like a pair of GP38s or SD40-2s in Sampage grade, you can open the window. What you have to do is to set the first trailing locomotive with the MU valve to lead, so that it is the leading at the rear, and that you can bail off all the independent brakes on the 2 or 3 locomotives at the end with the independent brake lever of the, what's it called, a SA26 valve, typically for the independent brake. And if you then go through the window with the external camera, you can bail off the air brakes on the rear pair. On Sampage grade this works great. It does not work with the AC44, because here you cannot go through the window and you cannot do anything with the external camera. But with external cameras and the rear, actually what you do in clinch field, the banking com doesn't work, right? It's one of the classic things, and you control the rear locomotives always with the external cameras through the window. And with external cameras it is really cool, and on clinch field you have to drive even, because you don't have a simulated driver in the rear, and copy what you do at front. This allows you actually to do the grading better. Because just imagine you are grading, you are running uphill, and then the front locomotives are already across the grade, while the locomotives at the rear are still in the incline. Then you would probably want the front locomotives to throttle down, while the locomotives at the rear are still providing propulsion. And this doesn't work with the simulated rear driver that just copies. So if you throttle down on the front locomotives, the simulated driver at the rear also throttles down. And with modern distributed power and stuff, this is not a problem. Then you have it computerized in a way that the locomotive can apply the optimum regardless of what the driver does at the front, but we don't have this simulated. We have just a driver copying what you do at the front and not touching the brake valves at all. Yes, so the external camera is a really nice thing on those. If you don't do it, well, then you don't have the effectiveness on the dynamic brakes on the rear locomotives as much as at the front. It still works most of the time, but to do it properly, you should also try to bail them off at the rear. That was my presentation for today. Thank you for listening to all of this. I will switch it off and go back to the locomotives. And I have a couple of them still here. Like for example, the F7. Juniper says, thank you for the presentation. Thank you so much for staying with me and listening to all of this. The F7, whether you use the Clinchfield variant or the Santa Fe variant, you have a similar thing like on the old SD40. You have this transition lever that you typically have to put to notch 1 if you want to drive. Reverse it to front, and then you can use the throttle to start your train. And if you want to use it as dynamic braking, just like on the SD40, you have to set it to B. Wait a bit, because it always takes a bit for the circuitry to adjust, and then the needle here on the ammeter moves just a tiny bit, and then you see, aha, now it is there, and then you can use the throttle to apply dynamic braking on this locomotive. Now it started raining on my at Cheyenne. Well, whatever. We will check it out without. So very important on the, what was it? I forgot the name, the scenario on Clinchfield, that is so great. A more modern locomotive, Norfolk Southern from the Horseshoe Curve. And you can see that the whole command stand looks much more modern. We already have an IETMS. The limited power, yes, Spectre, thank you very much. I was thinking distributed power, but no, it actually is not distributed, limited power it was. And there you need, in the end, when you run down your coal train, and if you don't want to have a runaway train, you actually have to use the dynamic braking on your F7, and if you don't know how that works, you will end up with a runaway train and can't do anything because the air brake won't be able to stop it. Actually, this would not be allowed anymore according to modern regulations, because you always have to have enough air brakes on your train. Is that an Inotrans, this locomotive? I don't think so. It is the, what is it called? The ES, the Eco on the of the GE, the General Electric, the successor of the AC44CW. And here still you have the dynamic brake lever, just like on the old Inotrans is the freight fare for... Ah, now your session. Inotrans, now I understand. Yes, almost. I have actually aligned as many as I can find. So still on this more modern thing, Evolution series, we still have the very old dynamic brake handle. Whereas on the F40 here, from Boston, Massachusetts Bay Transport Authority. If you look here, you won't find a lever for the dynamic brake. Actually, the lever has been removed and we have a metal plate covering the spot where it once has been, right? And still, if you use it, you will see that your ammeter here goes into the yellow braking range, that it can apply dynamic brakes. You will probably find somewhere EP. Don't mix it up with EP brake. Electro pneumatic brake is the air brake, but electrically controlled, so it doesn't have to do anything with the dynamic brakes. It's sometimes a bit confusing and people try to or tend to confuse it. Somewhere you typically find a switch where you can turn off the dynamic brake. I don't know if this locomotive has one. Blum. Probably not. This is for the EP brake. At any rate, if you, this is head and power here, I don't think that we have that here. Sometimes you even have a light for it turned off. Here you will have automatic blending with the EP brake without having a handle, without having to do anything. So you just select the brake force that you want with your 26C and the train is just applying the electric brake as it seems fit and is blending it in more or less properly. How can we get out of it again? Now we are so close together that we cannot close the door anymore. Doesn't matter. So that one is a British Class 66. And the interesting fact about, or one of the interesting facts about the Class 66 is that it is essentially an American built locomotive. What you can easily see if you look at the command stand here. You're sitting on the other side, obviously, not on the right but on the left, because we're driving on the left. But this command stand with the throttle here on the side looks very much like the American locomotives. And if you look for a dynamic brake, you won't find one, because this locomotive does not have a dynamic brake. It has the PBL, the French Poussoir Bouton Locomotive brake, which is essentially an EP thing where you control only the brake pipe with electronic commands on the locomotive, but the cars with the brake pipe pneumatically. It even has the stuff for the railhead cleaning. So, modern or more modern locomotive, British, still no EP brake. Are there no locomotives, no trains in the UK that have EP brakes? Sorry, dynamic brakes? Now I'm mixing it up myself. There are some trains. The A trains, the Japanese one, the Javelin, the Azuma, they actually have. The Pendolino, they also have dynamic brakes. And also this Networker here. If you look, for example, at this little button here, you can turn on regenerative braking. And this is actually a dynamic braking. And the 2020, Voyagers have rheostatic brakes. That's correct. But they are not in the game yet, at least not in Train Sim World, are they? I don't know why dynamic braking, electrodynamic braking is so not a thing on British trains, and especially on locomotives. But from what you can see, it is. While on German locomotives, like here on the Traxx 2, you classically have those two levers next to each other, the train brake and the electric brake. And the electric brake is our dynamic brake here, and you know that they are typically coupled in a way that if you move the train brake lever, you're also moving the lever for the e-brake accordingly on this generation of locomotives. But if you want, you can also move the e-brake lever separately and only use the e-brake if you're descending, for example. And then you will see the brake effort here on the meter going to the left in yellow typically. So that on this kind of locomotives you also have your dynamic braking. And look, this is I think the 68 have rheostatic brakes. That might very well be so, yeah. But I have not looked into the 68s. The Eurosprinter has the same setup here. Train brake, electric brake. If you look at the, what I don't have in my défilé here, the 110 or the 111, you will find also a separate lever for the dynamic brakes, for the e-brake. Vectron, still a bit different. You don't find. The only thing is what you can see here on the train brake, you don't have a second lever for the e-brake, but you have this button on top where you can switch on and off the electric brake blending that we have talked about. If you want e-brake or not with your train brake. If you have it active, what is the default setting, and you set it to whatever, then the e-brake will come into place first and the air brake will only compensate. Whereas here on the left side with the throttle, you have a combined power brake handle where you can actuate the dynamic brake separately by pulling it towards you. And this is the AFB. So a lot of different setups. The American Vectron, the American City Sprinter 64, has a quite similar setup, being a Vectron model, essentially. You also have a combined power and brake handle, but on the other hand, you don't have a German kind of driver brake valve, but one that reminds you of the 30A-CDW thing that you have on the GE locomotives typically, on the more modern ones. With combined independent and train brake. And here you have typically the brake blending coming with your auto brake, and if you want the e-brake alone, you can use this, and then you can see the effectiveness typically here on the effort meter. Even if you're not running, no, you can't. Whatever. Actually, the locomotive is running away. We don't want this happening. Even more, what we have to look at. This is a 155 from the German Democratic Republic. you can see that you don't have a separate handle for the e-brake, but still it has an e-brake, and it even has a brake force selector, and this brake force selector is for the e-brake only. So it will blend in e-brake if you use your driver's brake valve, and then you can select the amount of e-brake that is adding by this brake force selector here. Whereas on the 112 or the 143, I would have put up a 143, but those cannot be spawned without cars. Here you also don't find a lever for the e-brake, only for the train brake. I am not entirely sure if it applies brake blending here. What you can always do, your speed selector set to a lower speed that you are traveling, and then the e-brake will kick in and trying to slow you down, while with the force selector you can also adjust the amount of the brake force of the e-brake when trying to get to the speed that you selected on this here. So I don't even know how many different variants of e-brakes we can find in the game. The principle is always the same. The actual implementation can vary. Here with this AC4400CW, you even have on an American locomotive a setup where you can use the dynamic brake by putting it in the opposite direction of the acceleration. You can see that opposite to the German locomotives, here you have to pull the handle towards you to apply power and to pull it away from you to apply braking force. But the principle is the same. You have a combined handle for the dynamic brake and for the... why would we leave here? And for the throttle. So have we looked at everything that I put up here? I think we have. Last thing that I have here is my 406 in Tigerways livery. Do we have electronic brakes on the ICE? Of course we have. Do we have a brake lever for it? At least we are now out of this diesel noise. Do we find a brake lever? No, we have train brakes and we have throttle. We can't even put it into brakes. Still, can we find any indication that we have e-brakes? Yes, we can see it here. This is unfortunately the screen where we don't have it yet, but this here E means e-brakes. The lower one will be the pneumatic brakes, and WB for the eddy current brakes, the Wirbelstrombremse. I might want to delete my train here at this point and use a more modern version. Plop. Just deleted the train from underneath my ass. The tilting ICE, for example. If you look at the modernized version here. Yeah, unfortunately I cannot copy my livery for the 406 to other versions of the ICE. If you look at the same panel here, you can see actually what kind of brakes are activated at the moment. This train, unlike the 406, does not have eddy current, but it has a magnetic track brake, we have here. On the powered vehicles, only on the powered vehicles, the vehicles with driving motors obviously, we have e-brakes here in yellow, whereas at the moment are only applied the pneumatic brakes to keep the train in place. But if you drive with this screen open, then you can see that if you are actually slowing down, first the train will apply the e-brakes, and only if necessary it will add air brakes to slow the train down. Whereas the magnetic track brake you will typically only see if you go into an emergency brake, into a Schnellbremsung. Then you will also see the pink things for the magnetic track brakes. Well, yeah. I think that is what I wanted to do for the Emotrans. It's nice to see all those locomotives next to each other, right? Much nicer to see them as opposed to hear them. And now you gotta tell me what we are supposed to drive. Something with locos that would never meet in real life. You are so right. All my electric locomotives needed to be towed over. I actually wanted to put up a Swiss GE244 from Hermosa to show that on some locomotives you can even use the steering wheel type thing on your desk to actively go into dynamic braking with the wheel. But unfortunately they don't have narrow gauge tracks on their yard at Cheyenne, so I couldn't do that. Main menu. I would say we just have a train in Sherman Hill run down from Hermosa to Laramie while using the electric brakes. That won't be too complicated because this way we're just rolling down the hill for a bit and then that's it. To the trains, choose a route, Sherman Hill. This is where we just have been. And the timetable. Let's use the SD70ACe. What should be a EMD locomotive. And Cheyenne Hermosa, the superfruit. 29 minutes, maybe we can do that. CDRA says how whether you need a choke cracked, a spammer banished, or an odd signal dispatched really made my day. Very nice side says. Yeah, he's talking about our Daigoways site with all the videos that we have made so far. And obviously it will always be updated in a way that you can easily find the topic that you are looking for. But I'm sure all of us regular viewers should be featured there. AJ, I will tell her. Maybe she's not watching at the moment or is already asleep. But maybe we should do this for the regular viewers, for Spectre, for Lofty, for Perny, for Theodorus, for Super Paul. Yeah. Juniper. Obviously. Well, she mentioned the moderators so far. And I don't want to jinx too much, but maybe we will get a mention on the next roadmap stream with our website. So watch out for the next roadmap stream. Can't promise too much, but maybe this can actually happen. That would be well deserved, Spectre. So, Hermosa to Laramie Yard, Superfruit. AJ is awake but on mobile, says AJ. Alright. And she heard. Great. Okay. What do we have? 4 locos at the front, a lot of refrigerated cars, and at the end, do we have something at the end? We don't have any locomotives at the end. So, we are in a situation, like we said before, that if we are relying on dynamic brakes alone, then we have the whole train pushing against our 4 locomotives. And I think this works. So, the reverser is in, switches are on, headlights are on. Let's see if we have to, yeah, we are still at trail. This does not work. More options, operator controls, air brake lead, cut out, air brake cut in, lead and cut in. So now we should be able to release some independent brakes on, hold the train on all our 4 locomotives at the front. And do we have to do anything here? I just wanted to open the cabinet. This is one of the cabinets that you actually have to swing. EAD is the alerter on this train. The cab display computer is on. The cab signal fuse is off, what is a good thing because the cab signals here are, as we have discussed on the CSS stream, discussing the cab signals here. We always get restricted when we're only passing an approach signal, and I don't want to do this. Oh, there is another best viewer seller, and CD radar banned it. And Eternal Abyss, hey, you just came by to lurk a bit and say hi. Thank you so much, Abyss. I appreciate that. And what did not work? The banning did not work. Well, it doesn't matter. Let him advertise. Abyss, I really appreciate it. I know you're totally not into trains, so I really appreciate you dropping by and dropping a line in the chat. Did I forget something, or is our train already set up properly? Number board lights are on. We have all of it running. We have the lights on the outsides. We have the brake set up properly. We have a brake pipe pressure at the front of almost 90, at the rear at 77. We can wait a bit until we are beyond the 80 at the rear. It takes a bit to propagate through the whole train. Let's see if that actually confirms with what the end of train device is telling us. It says 77. And it says 77 of the end, at the end of train device. Alright. And see the radar band offending hangar. Oh yeah, that was good. And Abyss says always calming to listen to your voice. I just forgot to pop in usually. Forget to pop in usually. Well, that's nice to hear. As long as I don't do a face reveal you have to do with my soothing voice. 78 now at the rear. It actually takes a bit to inflate our brake pipe, but maybe we can just give it a go soonish. One other thing, actually, we've talked about the Code of Federal Regulation. One thing is that actually at the front end of the train you should have a reading about all the dynamic brake effort in the consist, not only on your locomotive, what would be the traction effort and then the dynamic braking effort here, but in the consist. Unfortunately, you don't get this in the game, so this does not actually comply with the Code of Federal Regulations. But also it does not comply with the Code of Federal Regulations in the way that we cannot do an integrity test. But that's okay. But that would be a thing that we can still add. And see the face reveal in real live stream meeting. Well, maybe sometime in the future. But we will have to get to a bit more subscribers in. Plot twist, says Abyss. Face is Thomas the Tank Engine. Well, Thomas the Tank Engine. We will see. We will see what happens in the future. Now I am actually really looking forward to the April roadmap stream and whether we actually get the mentioning with our website there. We are too international for the Thomas the Tank Engines, the City Raider. Well, that is the greatest thing about that we are so international. Well, I said 80. We wait for 80 for the rear to be inflated to 80 so that we do not wear off our brake shoes at the end. And here we are 80 at the rear. That means we can start. Signaler says we can go. We cannot really see a signal here. We have to lean out of the window to see a signal, and then we can't see it for our line because they are for the opposite line, for the opposite direction. And well, then forward. Let's get the driving motors running a bit. Since we are starting downhill, it is not so big a thing. End of train move, and we're picking up speed. We're in a 40 limit. We're too international for a meeting, says CD Radar. Well, actually, the two of us are not so far apart, are we? But you're right. Maybe we can arrange a meeting at TwitchCon next year or something like this. So, and now let's roll home to Laramie. When we get closer to the 30 miles, we can throttle down. Actually, running downhill should be enough to accelerate the train further. We at any rate have 8,207 tons in our consist. Always wait the 10 seconds before going into dynamic braking. And then let's see if we can slow this terrain down by dynamic brakes alone without touching the handle for the air brakes. You can see that we are running downhill, but not so super steep. And then we can set up the brake. You can see the tractive effort meter turning yellow. And as soon as we are setting our... we cannot use this while doing this. It takes a bit and then the train starts applying braking effort. It is still accelerating from what we can see here. Oops. In the accelerometer, and now we're aiming for our 40 while adjusting. The dynamic brake effort. The good thing with the dynamic brake, as soon as you are in the braking range, then you can really easily go high without being afraid to break something. That's a level crossing, huh? Can get a little bit more speed. And then we roll downhill with our 4 machines at the front. We provide enough mass and braking power to do this downhill run with the dynamics alone. Just have to pay attention where we are going to. And then we should be okay. Sherman Hill is the DLC that was actually given away for free on Steam for the Christmas specials. Unfortunately, I had it already, even on Steam. But nevertheless, it was a nice gift for everyone who did not have it before. When doing the full run from Cheyenne to Laramie or the other way around, it takes some time. Should maybe plan for 2 hours. So how much actual content do these DLC give, asked Abyss. Well, it depends on what kind of a DLC it is. There are route DLCs, there are locomotive DLCs. Some DLCs are only giving you new liveries, some are giving you scenarios or gameplay stuff, together with some more cars, for example. And also the routes are, they differ in length and complexity. But typically, on the typical route DLC, you get a route, you get maybe 1 or 2 new trains. At least that was the case in the early days. Sometimes you get 1 new train and a second train that is a variant of a train that existed before. And depending on what kind of route it is, if you have a route that goes from A to B, then it can be anything between 30 and 160 kilometers. You typically get a timetable with it that allows you to run the trains that come with the DLCs, and sometimes other DLCs are layering into this timetable. So I should say you get quite a lot of content, and if you are a player who is interested to look into a lot of things in the DLC, that you can easily spend all the time you can invest in playing the game in a handful of DLCs, I should say. And Thomas asked AJ, is actually coming as a DLC. I think it is a loco DLC because it is supposed to run on the West Somerset Railway. That was the alerter. And I think it is supposed to come quite soon, like next week or so. But this is a new thing with the Thomas DLC. And CD Radar says, oh, special sites starts very sadly. Yeah, totally. You mean the unique section. But I think it is the place that she deserves. AJ says she's gonna use all her channel points to make me play Thomas for like 10 weeks in a row. That means that I have to buy it first. Spectre says Thomas gameplay with the Hermosa jingle. Well, we'll see. At least I can tell you what wheel setup Thomas has. It is a classic 060 6-coupled setup. Would it be rude of me to add my highlights montage of the SimRail stream there? On the specials? I don't think it would be rude. What do you think, HA? You have to figure it out with HA how it is actually works. Yeah, why not on the specials? It can go under a header of its own. You always forget, or I always forget, to turn off the bell because you don't hear it in the cab. Even with the window open, you don't hear the bell in the cab. But you can see if it is on your screen. Bell? Bell, okay, not really. Because now you can see it. The bell icon. It's a bit confusing that you cannot use your keyboard shorts if you are zoomed in the screens. Yeah, but you can see using the dynamic brakes to go downhill, it's like using the throttle for driving uphill, just in yellow. And if you're going too fast, you have to turn it up. And if you're going too slow, you have to turn it down. See how long our train is. And all those cars are sitting in our back. Good thing that we've got 4 heavy locomotives. Don't forget to press the alerter every now and then. Still no end in sight. Spectre says, and all filled with fruits. Super fruits even. Is this an actually allowed length as abyss? Yes, it is. Precision scheduled railroading movements is lofty. You said it. And there is the end finally. Uh-huh. And we almost run into speeding. And we almost missed a 14L sequence. And Abyss says, alright, I've seen some that felt long in real life, but I guess our railroad just such as they couldn't support this anyway. No, our railroads wouldn't do that. But in America everything is bigger and longer, and railroading in America, when it comes to freight trains, is a different story altogether. Our trains are typically normally limited to something about 700 meters. If you're longer than 700 meters, I think if I remember correctly, you already have to subtract brake percentages. And you can see how long this train is. It is 5,306.8 feet. And now you can calculate it times 3. Divided by 3 to get the yards. And what was the factor to calculate how many yards are there in a mile? 1,600 or whatever. But you can have easily trains that are longer than a mile. It's 1,600 meters thereabouts, yes. And you don't have trains that long in Europe. In Europe sometimes you have, well, with trains that long you can actually manage to be in 3 countries at the same time on European railroads. Or even more. That would be cool, to be in 3 countries at the same time with your train. Train from the opposite. Dim your lights. Auto racks on the train that is coming from the opposite direction. 3 locomotives at the front. Auto racks. Now we can turn on the light again. Covered hoppers. 1 tank car, covered hoppers. Box cars. More tank cars. Yeah, those trains are long. Covered hoppers, more tank cars. Is it getting foggy? We still have 7 miles to Laramie. Boxcars. Covered hoppers, refrigerated cars, and it is actually raining in the desert. And one loco at the end. Well, it is not called a rain sim world for no reason. Even in the desert we are not safe. Ha ha. Well, actually, in real life, I like the rain. Raider says the idea of being at a crossing like a car and waiting for one train this long to pass through and then an even longer one coming from the other side. True. True enough. So, but we are actually closing in 5.6 miles. It's not that long anymore. Signals are still green though. How fast are we going? Asked AJ. We are going 38 miles. What is about 60 in kilometers per hour? Well, roughly at least. Turn off the bell. See, the radar says in subtle there is a Belize read error and it drains the whole pipe and then wait until it all fills up again. Well, if you want to have a brake pipe drained, then we need to turn on the cap signals. We've discussed this? No. Yeah. It is still dead, but it will come into existence as soon as we pass a non-green signal. Then the CSS side is actually working a bit like the ATC side should, but not here on this track. And then it will actually apply a penalty brake to slow us down and release it automatically again. For that we need to see something like this. Let's see what the next signal is giving us. Maybe already an advanced approach. Yes, flashing yellow over red, advanced approach. What should translate in a yellow over green probably, but will translate here in a green. For a weird reason. We had to acknowledge it. This is why we always get acknowledge and alert to reset on this key here. And this tells us that on the next signal we will get a non-flashing yellow over red approach, typically limiting us to 30 miles. But our cap signals will interpret it as a red over yellow restricted and limit us to 15 if we let it have its way, and it will also slow down us automatically to this speed. What is still not how those signals should work. This to me, it is so confusing with the different signaling rules in the US. Yes, it is confusing. But it is also so nice. I love the American signals. And the route signaling is actually quite simple. The ones from Boston Providence. Well, the NORAC has so many different signals. And speed signaling is much more difficult than the route signaling. Especially if you look at the dwarf variants then. And I think you can grasp it after a while, but you really have to go through it quite a lot, and I've never really understood it enough before I started doing those videos and had to make those presentations myself. So we're approaching a yellow over red approach. This is why I slowed down to 30. What normally should be totally enough. But what our cap signaling system will not like anyway. And it will apply air brake. You will see that this 90 number here will drop. Until we have slowed down to 15. And then we will release. See, on the CCS, red over yellow restricting what is actually too restrictive. And now it is dropping us. And it is giving us a penalty brake to slow us down to 15. And then it will release it again. You can see how the train automatically lowered the equalizing reservoir to 63 and the brake pipe is following. Red leader hails everyone. Nice to see you. I always drive US trains with the cheat sheet for the route because of that. So, brake pipe is already back at 90, at least at the front. At the rear it is not yet. This is why I'm applying some power to stretch my train. And to get it up to 15 so that we can go the last 9,000 feet. And normally, without the cap signaling, this should be enough to roll with 30 here. You because this is what the approach is giving us. But if we accelerate to 30, then the speed control on the cab signaling system will interfere again and slow us down. Spectres is... Yes, there are nice signaling charts online as PDFs. Unfortunately, there's a pause button, unlike in real life. That's true as well. Well, the most important thing is to know whether you are in speed signaling territory or in route signaling territory. And then most of the time everything explains itself for you. This is one thing that I like so much about the Peninsula Corridor, that you have route signaling and speed signaling in the same DLC. No. So, rolling far enough so that our whole train can be on this track. Probably can turn off the wipers again. So then we have to make a judgment call when to yank in the brakes for stopping in front of the red signal. Maybe 150 feet. With a bit of stretch braking at the end. Love how those cars are going around the corner there. Whee! Oops, don't forget the alerter. So, end of our train has arrived as well. Having to clear the switch. And I think behind this overpass is our red signal that we are aiming for. Last 1,000 yards. Nice pile up of cars over there. Junkyard is always a nice thing to see. No, I need more. I need more. There's the red light coming. Ooh. Will we make it? Just like this. Okay. That's that. So we have seen we can just roll down the hill with the dynamic brakes alone. And then obviously for stopping the train we need the air brakes to hold it in place. Guys, that was the stream for today about the electrodynamic brake. Still missing in our collection of brake videos, and thank you very much for staying with me, for all the ongoing support. And 2 hours 3 minutes, we hit the mark quite well today. Thank you so much. Have a nice time. Be nice to each other and see you soon.